All right, so in this video, we're going to be looking at hydrostatic pressure and force. And our first question is find the hydrostatic force at the bottom of the tank. So we want to see how much force is being applied to the bottom of this little tank. And where that comes from is the weight. So if you think about yourself, there's a little scale here, or let's do me instead. And I stand on this scale. And then the scale reads 200 pounds. What that means is my body is applying 200 pounds of weight or force to the bottom of that scale, to the top, well, that scale itself, not the bottom. And we want to see how that applies here. So if you think about it, we can look at this as a cube. So the weight density of water, represented by delta here, is 62.5 pounds per cubic foot. So what it means is that little cube right there weighs 62.5 pounds. So if we want to find the total force, what we need is the total weight of all that water that's added up. So if we just start making more cubes, right, and then adding them together, it'll tell us the total weight, which is our force. So what we get here is a force formula that is our delta, which is the weight of a cube, times our volume, which is the number of cubes. So this is weight of 1 cube times number of cubes. And that would give us our total force. So it's 62.5 times, and then our volume is just length times width times height. So 5 times 4 times 6. You plug that in the calculator, and we end up with is 7,500 pounds. So there's 7,500 pounds of force being applied to the bottom of that tank. Now, we're going to need a different formula later, so we're going to modify it now. So there's my delta times. What we can do is break the volume up into two letters, depth and area. So this is 0, and this is 6, and this represents our depth. And then down here is the area of the plate that we're putting pressure on. So you can see that the volume would be 5 times 4 times 6. So what it is the area times the depth. It's a different way of having the formula. Next step is pressure. So what pressure is the force divided by the area. It's the force per square foot. So if you take and break this into 1 foot, right? That's our pressure. 1 square foot. So it's the force per square foot. So we want to take our force now and divide it by the area, and it'll tell us the pressure that's being applied there. So if we take our force of 7,500, we divide it by the area, which is 5 times 4, we get 375. And now this is units. So this is pounds up here, and this would be feet squared because it's feet times feet. So we end up with pounds per square foot. So what that means is there's that pressure here, right? And the way you can look at it is if you take all those pressures and you added them up, then you would get the force. So that's how they're related. You take all the pressures being applied to that plate, right? And there are 20 of them, because 5 times 4 is 20. And you multiply by the 375, you would go right back to force. So that's how they're related. Pressure is the force per square foot, and force is all of those pressures added up. Now, we need another formula. So if we say pressure, and we take our delta dA, and we divide it by A, we end up with delta D. So you can find the pressure at any depth by just taking your weight density and multiplying it by the depth. So you could say 6 times 62.5, and you get 375. Because the A just cancels. All right, now let's take and put this together. So what we need to do is find the hydrostatic force on the side here. So if you think about it, we've got this one plate that we can divide it up. We want the force of the entire thing, but we can break it up into parts. Because what's happening is if that's our depth of 0, here is our depth of 6, right? And we can call this X for depth. But at different heights, you have different pressures, like this. So when we are at the top, we can just assume that this is 0, because it has no depth. And then all the way to the bottom, that's a depth of 6, so we know that one was 375. So it's going from 0 to 375. So at any point along this wall, we have a different force that's being applied because we have a different pressure. So you can think of it two ways. We can take our force, which is delta dA, or you can think of it as your pressure. We know the pressure here that's being exhibited to this, that is delta D, right? And so if that's the pressure, remember, to make the force, all you have to do is multiply it by the area, and that's what we're doing. So that's how the formula is being made. It's the pressure that's being applied, and then times the area of that plate would give us the force. So we need to make a formula for that plate. Now we know it's x, so we have a width of dx since we have x. Now we can find the length of the plate because that's just 4. And so now we have the area. Area is length times width. So this is 4 dx. Now this d has nothing to do with it. It's not the change in a. It's just literally d and a, because this is our force formula. We haven't gotten there. It would be like this, delta a. But we're not doing that. So now we go to our depth. And so our depth of that plate would be x. So if you think about it, this one plate has a depth of x, a width of 4, and a length of 4, and a width of dx. So that would be the force on that one plate. Force equals delta x 4 dx. So if we take our integral now and we go 4 delta x dx, and we go from 0 to 6, that would give us all the forces. So you can always check your formulas very, very quickly. At the top, we know it's 0. So we have a depth of 0, a width of 4. And you can see that, 0 right here for x, and then 4. So at the top one, if we have 4 delta x dx, right, then we have a depth of 0. Then we would get 4 delta times 0 dx, which is 0. And if we had the bottom one, we have a depth of 6, right? Then what we're getting is 4 delta 6 dx. So that formula, we'll be plugging in the depth as we move down. The width is always constant at 4, and the thickness is always dx. So if we plug that in our calculator now, we get 4,500 pounds. So that is the force that's being applied to that wall. So now if you think about moving it, and we do the other side, this one right there, that one now has a width of 5. So all we would have to do is go, okay, my width is now 5 delta x dx, and that would give me 5,625 pounds. And now I'm moving the numbers around. It doesn't matter how you write it. You can do delta 4x dx. Remember, it's just multiplication. Delta 5x dx. However you want to write it. But this is what we're going to be doing. So if you're given a constant value, you can just plug it in. If we're giving a variable here, we're going to have to use an integral because, well, that pressure is going to vary as we move from top to bottom. All right. At the bottom, you have some more formulas for it. We're going to be dealing with metric as well, and that's when we're going to get into rho g, which is our new density, the new weight density, which would be the density of water. In this case is 1,000 times gravity, which is 9.8, and we'll talk about that in another video. But we're going to be dealing with this when we talk about feet.